Why does mathematics work? Why is it so useful? Is mathematics invented or discovered? I happen to think we discover it rather than invent it, but it depends on one's philosophical presuppositions what conclusions one will draw.
One of the most celebrated discoverers of the role of mathematics in nature was a young Italian merchant son called Fibonacci.
Fibonacci was a 12th century mathematician living in Pisa, and he came up with a sequence which is prevalent in nature today in one form or another, known as the Fibonacci sequence: 1, 1, 2, 3, 5, 8, and so on.
Each number in the sequence is the sum of the two previous numbers. So the next number after 1 will be 1 because there was nothing before it. The number after that will be 2, 1 plus 1. After that will be 3, 2 plus 1. Then 5, then 8, then 13, 21, 34, 55, 89, 144, and so on.
The whole sequence appears again and again and again in one form or another with surprising regularity. And it is amazing. Nobody really knows why this particular sequence is so important in nature, but there it is. That's what we see. If you look at the distribution of seeds on a sunflower head, you see these wonderful spirals, which are in a sense optical illusions because they're not representative of the order in which those seeds were developed. Nevertheless, the number going clockwise and the number going anti-clockwise are 95% of the time adjacent terms in a Fibonacci sequence. And it's just amazing.
But there's more to the Fibonacci sequence than the arrangement of seeds on a sunflower head. The ratio of successive numbers in the sequence gets closer and closer to a rather special value known as the golden number.
This golden number, 1 plus the square root of 5, all divided by 2, is a natural consequence of the geometry of a regular pentagon. If you draw a regular pentagon and you join up the corners, these chords, these lines joining the corners, intersect one another in a ratio that can be shown to be this golden number. The ratio of the larger part of that chord to the smaller part is the same as the whole length of the chord divided by the larger part, approximately 1.618, the golden number. The golden ratio is a linear measure in the sense that it's a ratio of two lengths. If one translates this to the geometry of a circle, one can get something called a golden angle. It turns out to be approximately 137.5 degrees. And that, again, figures quite commonly in nature in the arrangement of leaves.
The most effective arrangement of leaves on a stem is when the new ones sprout at precisely the golden angle from the one below. One consequence appears to be minimal blocking of sunlight from leaves below when the sun is high.
If you look at a cactus from above, some types of cactus at least, I have a very good photograph of one with a picture of my shoe there as well, which you can determine that this golden angle is approximately represented as the leaves grew from one to another, and so the successive leaves fill the space with that angle from the previous leaf, and it's quite magnificent. I've measured some of these, and while I can't measure them accurately, it's pretty darn good approximation to 137.5 degrees.
The more you look at natural phenomena, the more you see the evidence of golden ratios, golden angles, and the Fibonacci sequence at work. And often that will result in the emergence of spirals.
They're everywhere, if you care to look. Seashells, the nautilus shell, the shell of a snail. You can actually relate this spiral approximately to the golden ratio. If we go back to our golden rectangle, which has long side approximately 1.618 short side 1, and you cut off a square, what you have left in that rectangle is another rectangle, a smaller one, which is also a golden rectangle. The relationship between the areas of the squares is extremely interesting. They are in the ratio of successive Fibonacci numbers. We might start with 1, and then 1, and then 2, and then area 3, and then area 5, and then area 8, and area 13, and so on. And if you keep doing that, and then join corner to corner with an arc of a circle, you get an approximate equiangular spiral. And this is certainly very reminiscent of these spirals, particularly the nautilus shell that we see in nature. So once again, these numbers are almost ubiquitous. And one of these days I'm going to ask God why.
One of the most enduring puzzles of mathematics in nature relates to the patterns and markings we see on animals. A leopard's spots, a zebra's stripes, and so on. It fell to one of the greatest mathematicians of the 20th century, Alan Turing, to shed light on the topic.
He was a genius. He published one paper, and one only, on the chemical basis of morphogenesis. That was his only foray into biology, but it was profound, it was seminal. Morphogenesis relates in biological terms to the various chemical changes that may take place in an embryo that will ultimately lead to patterns in the adult creature. The equations are quite complicated, but mathematicians have found that by varying the parameters in these equations, you can get spots, you can get stripes, you can get uniform colors.
These studies have helped answer some age-old questions, including whether zebras are white horses with black stripes or black horses with white stripes. People used to think that they were black striped white horses, but the prevailing view is now the opposite. Zebra embryos are completely black. The white stripes appear during the last embryonic stage. So zebras, it seems, are black horses with white stripes. But not all of the colours in nature are created by the interaction of chemical pigments in an animal's skin. Some colours are created by microscopic structures that split white sunlight into its component colours. It's a phenomenon known as iridescence. Many birds and insects display these beautiful colours. Iridescence. I love that word because it's derived from a Greek word for rainbow, iris or iridos. And over the years I've studied rainbows in great detail. Rainbows are all about some basic and yet very subtle geometry, and they will only occur when certain very specific conditions are met.
The sun has to be shining, there has to be rain somewhere, and if the conditions are right, if the sun is not too high in the sky, then if you stand with your back to the sun, the sunlight is scattered by the raindrops ahead of you, and it's scattered in all directions, but there's a concentration of the light that is refracted inside the raindrop, reflected from the backside of the drop, and refracted out again. The colours you see are from different raindrops. There's myriads of raindrops, so it's a cumulative effect. A good portion of them will scatter red into your eye, a good proportion will scatter green, orange, whatever. In a sense, a rainbow is a highly exotic image of the sun. I just love rainbows. I think most people probably do. If I can go on to another phenomenon which is related, the glory. If you've ever flown on a plane and been on the shadow side of the plane, above cloud, you may well have noticed the shadow of the plane surrounded by circular coloured rings. And that's backscattering of light by cloud droplets. The smaller the cloud droplets are, the larger the radius of the glory. This is an amazing phenomenon.
And the more you look into these atmospheric optical phenomena, the more fascinating they become. Interactions between sunlight and water droplets, sunlight and ice crystals, and always the all-important geometrical configurations that link you, the observer, the sun, and whatever water droplets or ice crystals are creating the effect. So you get sun halos, moon halos, fog bows, sun dogs, circumzenithal arcs, circumhorizon arcs, and so on. It's a mathematical feast. As I often say, mathematics and nature is the greatest show on earth.
And what thrills me is when a student, and this happens quite a lot, will either come to me at the end of a class or sometimes after the course is over and will show me a picture they've taken or sketch out something they've seen, and they're excited by it and they don't perhaps understand what was going on. What was happening here, they say, and I say, well, I wasn't there, I don't know, but here's a possibility, here's what I suspect. They're actually thinking, they're taking this stuff outside into the greatest free show on earth, and they're thinking about it, and they're thinking about the underlying principles, and whether or not they're correct, it doesn't matter to that degree. It's the fact that they're thinking and their curiosity has been aroused. And so I feel like I've made a difference, however small, in that student's life.